Welcome back. Now we're going to move on to part B. So we've found our boundary conditions in terms of requirements on x of x for the separation of variables. And now we want to find the separated solutions for x that satisfy the boundary conditions. And we want to explain carefully why we can reject some of the solutions based on the boundary conditions. So we've gotten our partial differential equation. We've already got solutions, so now it's merely a question of determining which of these solutions satisfy the boundary conditions and what constraints they may be placed under. So satisfy and constraint. So let's start off with the first set of solutions. Now we're going to assume that the boundary conditions are only on x, and that's safe given what we were given in part 1. So let's start off with x sub x is equal to a e to the kt, kx, plus be to the negative kx. Copy that correctly. So try this case. So our boundary conditions are expressed in terms of the derivative of x prime. So let's find x prime of x. So we're going to take the derivative of this. So we've got a k e to the kx plus b negative k e to the negative kx. And let's evaluate that at boundary condition 1, which says that little x is equal to 0. It's got to be equal to 0. For this particular boundary condition, that translates to x prime of 0 is equal to a k e to the k times 0 minus bk, because we're just popping that negative sign out, e to the negative k times 0. So this quantity simplifies to 1. This quantity simplifies to 1. And so for this boundary condition, we have x prime of 0 is equal to ak minus bk. So this gives us the constraint that ak is equal to bk. So a is equal to b. This is not giving us any restriction on k. Other than perhaps we're assuming that it's non-zero, which for this particular separation of variables, coupling constant between the two separations, we're assuming that anyway. Other than k not equal to 0, which is true anyway. So now we've got boundary condition 2, which from up here was that x, nope. Still getting the hang of this. X prime, x equal to 1 was also equal to 0. So now we can use the simplified form of x prime of x, given that a is equal to b, to say that we've got ae to the kx plus b. Oh, that is wrong. That is totally incorrect. There, I'm not even paying attention. Okay, we want to use a k e to the kx minus k a e to the kx, because we want to use x prime and we don't want to use x. It's really easy to make a mistake here. So we substitute in for little x is equal to 1, and what do we get? We get a k e to the k times 1 minus k a e, oh, forgot a negative sign there, negative k times 1, and that's equal to 0. We're just getting that from that, and we're getting that from that. So we get that x prime x is equal to 1 gives us, well, we've got a common term of a, and we've got a common term of k. We've got e to the k minus e to the negative k. is equal to 0. So that means that A could be 0, K could be 0, or this quantity e to the k, e to the negative k is 0. So we know that this is not 0, and that this is not 0. So that means that our quantity A, in order to satisfy this equation, A must be equal to 0 to satisfy, and it helps if I could spell, both BC's. So in this case, the only solution has A is equal to 0, which is to say that x of x is equal to 0, which is the trivial solution, so we can reject. And the reason we can reject this is because taking our separation of variables quantity and multiplying it by 0 just gives us 0, and we can always add 0 on as a solution. So there's nothing terribly remarkable about that. So we can reject those. Now, let's try what's our second option here. The linear solution, ax plus b. So again, we're going to state that x of x is ax plus b, but what we're actually interested in is the derivative. So we're going to take the derivative of this linear equation, and that's just going to give us the constant a. Now I go to boundary condition 1, which was that x prime, x is equal to 0, is 0. I'm going to substitute in, say x prime of x is just equal to a. Well, that's just got to be 0. And that is, in fact, let's tidy that up. X prime x is equal to 0 is equal to a is equal to 0. So a must be equal to 0. So likewise for boundary condition 2, x prime, let's clean that up. X prime x is equal to 1. Now that's also equal to a, equal to 0. We get the exact same thing. So we've got a condition that a is equal to 0, and we've got no condition on b. Again, these boundary conditions were just stated purely in terms of the derivatives, and because they're stated in terms of the derivatives, a is going to be set to 0, but b can be anything we want. So we can't reject the linear solutions, but we can restrict it to them being constant. And it helps when I can spell. So this means in our final solution, we need to have constant terms available. So let's move on to our third option here. So let's just, so that we don't, that's a no, that's a yes. And now we've got our third option, which is a cosine kx plus b sine kx. Let's go all the way down here. So now we're going to try x of x is equal to a cosine kx plus b sine kx. And again, we're going to look at the derivative of this. We're going to have negative a k sine kx, and then we're going to have plus bk cosine of kx. So we've just taken the derivative here, and now I'm going to evaluate at boundary condition 1, which is x prime little x is equal to 0, gives me negative a k sine k times 0 plus bk cosine k times 0. That was unhelpful and uninteresting. So the key point here is that that evaluates to 0. That evaluates to 0. So the sine evaluates to 0, but the cosine of 0 evaluates to 1. So when we're looking at x is equal to 0, all of a sudden this whole term goes away, and we've just got bk. But we know from the boundary condition that that's equal to 0, so that's equal to 0. So either b or k is equal to 0. Now, if k is equal to 0, x of x just becomes a cosine k, but k is equal to 0. 0 times x plus b sine k, and I did it again. 0 times x. Well, this is just 0, so we don't care about b. This would be 1. So what do we get? So if k is equal to 0, x of x is just a constant. And we know that that's an okay solution from up here, but we also know for this particular case, k is not equal to 0. So since k is not equal to 0, we know that b is equal to 0. So keep in mind that the b was the sine terms here. So now we can restate x prime of x for BC2. And let's change that a little bit. So we're interested in x prime of x at x is equal to 1. Let's just double check our boundary conditions here. BC2, yep, that's what we're doing, is equal to 0. X prime, x is equal to 1. So we can now ignore the sine term, and we can just say that that's equal to negative a k sine k times 1 is equal to 0, enforcing that boundary condition. So our options are that a is equal to 0, k is equal to 0, or sine of k is equal to 0. So a is equal to 0, or k is equal to 0, or sine of k is equal to 0. So again, we know that in this case, we get trivial solutions. In the second case, we know that we're not interested in the k is equal to 0 action. So instead, we get that we have a condition on k, and we have no conditions on a in this case. So what is the sine of k is equal to 0 thing? So let's go and draw our little sine cosine diagram so that we can be clear about what we're doing. And that's an okay circle. So I'm going to set k is equal to theta. And here's a little unit circle. So the key thing is we want to know when sine of k is equal to 0. So that is these points here. So sine is the elevation. Now the reason that I do this is in case our boundary condition, say it wasn't at 1, say it was at 2.5 or 47. or something annoying like that. This allows me to convert between theta, where I've got a real good intuition, and k, which is what I care about. So since sine of k is equal to 0, this occurs when k is equal to 0, which we don't care about, pi, 2 pi, 3 pi, 4 pi, etc. Now, keeping in mind that we don't want that 0 case, we've got k is equal to some number n times pi for n integer and positive. Or if we want to be fancy, we draw that with a little symbol there, which I did a really bad job at. Let's try that again. Ah, there we go. So that's just a snazzy way of saying that n sits in the set of positive integers. All right. So have we succeeded? So the other important thing here is we want to be sure to highlight our conclusions. So trivial solution can reject. Here we can restrict it to only constants. And here, yes, these solutions are included. And in particular, we have no conditions on A, and we have this restriction on K from our boundary conditions. All right.